Alright, so let's do a electric field problem for AP Physics C, electricity and magnetism. Here we go. So we have a triangle here with three charges, all with different values here. And so we are going to try and find the electric field. And so we're going to actually divide this into two. We're going to find the electric field in the x and the electric field in the y direction. Okay, so we're going to define a coordinate system. And this is very arbitrary. We're just going to say this is the positive x direction. And um, let's let's just keep this as y. And so to make this relatively easy, so we want to find the electric field in the x direction and the electric field in the y direction, centered at this midpoint between this 8 microcoulomb charge and this negative 5 microcoulomb charge. So from the equation sheet, we know that the electric field is equal to the force of an electric field divided by Q. Fe divided by Q. Well, we know that Fe is just K Q1 Q2 R squared, again from the equation sheet. Q over R squared. So we can substitute this back in here and find that the electric field in a direction, let's make this a bit smaller. So the electric field in a singular direction is going to be K Q over R squared. So let's first look at here. So we want to find this value for R. And so this is a right triangle because we divided it halfway down the middle. This is also an equilateral triangle because each of the side lengths of this triangle are 5 meters or 0.5 meters. And so this area, this length right here is 0.25 meters, which will be helpful when we do the x components. So we could say that R, if we wanted to call this R1, is just R1 is just the square root of 0.5 squared minus 0.25 squared. That's just from Pythagorean theorem. So this is this R value. And so now we could start substituting. So now we know this R, which is alright, which is approximately 0.43. And so now we can say that the electric field in the y direction is going to be equal to K, which is 9 times 10 to the ninth and then the units are newtons. That looks like a little micro symbol. Newtons, come on now, in newtons times meter squared per coulomb squared. So this is the electric constant K. And then we're going to multiply it by Q, which, because we're doing the y direction, and these are equidistant, they are not affecting the y value in any way. At this point, as soon as it moves down, due to the electric force, they will affect it. But at this moment in time, they are not affecting the y direction. So we're going to say 3 times 10 to the micro is 10 to the negative 6 coulombs. All right, and then we're going to divide that by, and then the radius, which is what we established, 0.43, 3 squared. And so let me go show this into a calculator, which is going to be about 1.5 times 10 to the 5th, and the units are newtons per coulomb. So newtons per coulomb. Right, so now we're going to look at the x value. And so the electric field in a direction can be the sum of the electric fields. So for example, we have, if we wanted to do the electric field just by this particle, would be K times 8 microcoulombs divided by 0.25 squared. And then we could also add that with the other one. So and the electric field will point away from positive charge, so, and to negative charge. So these two electric fields can be added. So we're going to write 2 of these little things, and we're going to add them together. So we're going to do 9 times 10 to the 9th. This is meters. So this meter squared cancels with this meter squared. This coulomb squared cancels with a coulomb. So there's going to be a coulomb on the bottom, and then newtons remains on the top. So that's how these newtons per coulomb are established. So we're going to just not write the units. So so this first one, we're going to do times, I guess, this 8 microcoulomb. So 8 times 10 to the negative 6. Negative 6 over 0.25 squared to 5 squared. And then we're going to add this to the other one. And so, because it's going to the right, then we can add these two electric fields. So 9 times 10 to the 9th times. And because we know that the direction is positive in the end, that we can, or it's going towards the negative charge, that we could just leave the negative off of it. So 5 times 10 to the negative 6 and 0.25 squared. And so this will be our net electric field in the x direction. And so I'm going to shove this into a calculator. Alright, so this is about 1.9 times 10 to the 6th newtons per coulomb. And this is how you would do an electric field problem like this.